My dear students, welcome to the linear Algebra 1 OMT 112. Now, we are going to see the knowledge area 4, which covers spanning sets, bases, and linear transformation. Okay. In this lecture, we are going to cover these three things: spanning sets, bases, and linear transformation. Okay, let's see what are spanning sets. By definition, let's say we have a vector space V, and we have a set which is a subset of vector space V, call it S, with vector V1 up to Vn. And also, within this vector space V, we have a set of vectors W, which all these vectors are the linear combinations of the vectors in a set S. Then W is called the span of vectors which are in a set S, vector 1 up to vector n. And this can be denoted by W equal to span in bracket S, or W equal to span in curved bracket V1, V2 at Vn. We also say that the vectors V1, V2 up to Vn span in W. Okay, here we have an example. We are required to determine whether the vectors V1, V2, and V3 span in R subspace 3. Okay, solution. So, here we need to check if there exist scalars C1, C2, and C3 such that these scalars should be the real numbers, such that scalar 1 times the first vector, scalar 2 times the second vector, scalar 3 times the third vector, which is V3, equal to one of the vector which has the following entries xy, and z, where these xy and z are real numbers. So if these scalars exist, then we say that these three vectors span in R3 space. Okay, so just continuing to find the solution. Here, these x, y, and r are just n real numbers, and the C1, C2, and C3 are just n real numbers. So here, we first multiply these scalars with their respective vectors given, vector 1, vector 2, and vector 3. So after multiplying this one, and then we add them together, vector single vector like this one. So look at here, we have three unknown numbers, and taking this as general n real numbers. So now we can take this one outside and solve this simultaneously as a system of linear equations. So after solving, if you solve this, you will find that the system has no solution. If it has no solution, therefore, the scalars C1, C2, and 3 do not exist. And therefore, we conclude that the vectors V1, vector V2, and vector V3 do not span R3 space. Okay, that was just the first example on how to show that the three vectors which are in 3 dimensions span in R3 space. So let's now we have this another question. Example 2. Consider the following set C of vectors, in R3 space. Vector, this one, and this one. It's a set of 3 vectors. And now, prove that the span of the vector, the span of the set is all of R3 space. We just use the same procedure we have seen in the first example. To show that this span in R3 space, we have to find if there are existing 3 scalars, C1, C2, 3, namely C1, C2, 3, such that C1 times vector 1, which is this one, C2 times vector 2, this one, adding here, plus C3 times vector 3 will give us one of the vector in R3 space, which is generally represented as a vector with the entries x, y, x, y, and z. And then this, after multiplying, we can combine them and get a system of linear equations. And by solving this one, because x and y and z are not specifically given, we have just taken is any of the vector in R3 space which has these entries x, y, and z. So here what we are going to solve, we are going to solve for C1, C2, and C3 in terms of x, y, and z. So solving by using any method of solving the system of the linear equations. Hope every student is aware of solving this system. You can use any method. So for me here, by solving, I just obtain C1 equal this one, C2 equal this one, and C3 this one. X, Y, and Z can be any real number. So since this solution exists, now we say that the vectors, the set of vectors, let's go back. This set of vectors in R3 span in R3. Okay. We have another example here. So this is like quite different. We are asking to find. We have given this vector. We have to find this vector in the span of this one. In this vector, the span of this one. We have already seen that if you have given a vector space, the span in that vector space are all set of linear combinations of the vectors in that vector space. So just here we have just given a specific vector, this one. We need to see that if this vector span these vectors. To show that this vector span, in the span of these vectors, we need to find if there exist scalars that can be multiplied, this one plus this one plus this one equal to this one. Or in another way, we need to show that this vector can be written, as a linear combination of these vectors. Okay, after showing that this vector can be written as a linear combination of this one, therefore, you have already shown that this vector is in the span of those three vectors. Okay, like I've shown here, and so, but just solving this system of linear equations and then getting that C1, C2, and C3 exist. And therefore, we conclude that this vector is in the span of S of vectors. Also, the same example here in example 4, I give you, my students, as exercise for you. Okay, let's continue. Basis. Okay. Suppose, by definition, you have given a set of vectors, call it S. And this set of vectors is a subspace or is a subset of the vector space V. So when we call this is a basis. SC is called basis for singular, basis for plural. For V, if satisfies the following axioms or conditions. The first axiom that it has to satisfy that SC should be S spans the vectors, the vector space V. If S spans the vector space V and S is a linear independent set of the vectors in V, therefore SC is called basis. Okay, this is an example. Let's go see an example. Students, let's see this example to determine if the vectors V1, V2, and V3 will be basis for R3 space. Solution. Remember, to show that these three vectors will be basis for R3 space, we need to show if these vectors, three vectors, satisfies two axioms. One of the axioms is we need to show that the three vectors span R3 space. How can we show that the three vectors span R3 space? We show it by finding if there are existing scalars, or I mean n3 real numbers, such that these three vectors can be written as a linear combination. These three vectors can be written in this form, where this gives a linear combination of vector W, where vector W is any vector in 3 space. Let's say it has these 3 entries, A, B, and C. So, my dear students, let's solve this one. Now, we need to show that these 3 vectors can be written as a linear combination of n of the vector in R3 space, which is W, equal to C1 vector 1 plus C2 times vector 2 plus C3 times vector 3. Now, remember, we have said, we have read that W to be this one, A, B, and C, where A, B, and C are real numbers. So now, we write here A, B, C, and C1. Vector 1 has entries 1, negative 1, 1. Vector 2 has entries 0, 1, 2. And vector 3 has entries 3, 0, and 1. Okay, this C1. Now, multiplying this one here, and this one here, and this one here, and adding all of them, as you have been doing in other examples in the past lecture. So now, here we get C1, this time that's C1, this is 0, 3 times C3, this is 3, 3, this is 3. Okay, this one here is negative C1, this time this one, plus C2, this is 0. This C1 plus 2, C2 plus C3 equal to vector W, which has entries A, B, and C. So we can solve this as a system of linear equations by just writing C1 plus 3 equal to A. Negative C1 plus C2 equal to B. And C1 plus 2, C2 plus C3 equal to C. So you can solve this one by using an method of solving the system of linear equations. By using either the inverse matrix method, by using either Cramer's rule, by using either the row reduction. But here, in my solution, I obtained that because here we want to find if C exists. C1, I obtained that C1 equal to C1 equal to 5A minus 6Y minus 3Z. Sorry. 5A, 6B minus 3C over H. And also I obtain C2 equal to 5A plus 2B. 5A plus 2B minus 3C over H also. And then C3 equal to C3 equal to A plus 2B plus C over A. Remember that A, B, C are n real numbers. So since these scalars C1, C2, and C3 existing, therefore, here we have already shown the first property that it is satisfied that the three vectors span R3 space. Okay, my dear students, let's again see if the second axiom is satisfied to see if these three vectors are linearly independent. Okay. Okay, let's see the second property. The second property, we need to show that the vectors are linear independent. By showing that there are existing scalars C1, C2, and 3 real numbers such that a zero vector can be written as a linear combination of these three vectors, that C1 1 plus C2 V2 plus C3 V3 is equal to 0. Okay, and remember 0 is a zero vector. So substituting the three vectors C1 times vector 1, 1, 1, 1, plus C2 and the vector second vector 0, 1, 2, and plus 3 and the third vector which has entry 3, 0, and 1. Okay, dear students, here we are going to find the value of the scalars C1, C2, and C3. And these vectors, to be linearly independent, we must find that C1, C2, and 3 are all equal to 0. So let's continue. Multiplying C inside, I get C1, here is 0, and here plus 3, C3. And the second row will be C1 plus C2 because it's 0. And the third row, C1 plus 2C2 plus 3 equal to, remember my dear students that here, the 0 we put here is a 0 vector of 3 entries because the other vectors are 3 entries. Now here is 0, 0, 0. Solving this as a system of linear equations, we let's write the linear system of linear equations C1 plus 3 C3 equal to 0, C1 plus C2 equal to 0, C1 plus 2 C2 plus C3 equal to 0. If you solve this one by using element method, you get that C1 equal to 0, C2 equal to 0, and C3 equal to 0. Since these scalars exist now and they are all equal to 0, now we say that these three vectors are linearly independent. And because all the two properties, four axioms, has been satisfied, now we conclude that these three vectors are basis for R3. Okay, my dear students, let's continue with the next subtopic called the linear transformations. What is linear transformation? By definition, is the mapping from one vector space to another vector space that satisfies these two axioms, where C is any real number. In other way, we call it a scalar. So in here, this definition here, T represents a linear transformation or a mapping from one vector space Rn to the other vector space Rm. And therefore, the vectors u and v should be the elements in the first vector space Rn. So here is one of the example to determine if the following transformation are linear or not. So we have A and B. We have transformation T and transformation W. Okay, let's see this example. Solution. To show that this is a linear transformation, we need to show that it satisfies the two axioms we have mentioned already, which is this one and this one. And remember that this function, I mean this T, is mapping from the vector, the set of vectors which are in R2 space to the set of vectors which are in R3 space. So to show this one, we have first to learn two vectors, and because here from the definition we need to have just two vectors to show the satisfying of these axioms. The first axiom needs two vectors from this this vector space. And the third axiom needs just one vector and a scalar. So here we are writing two vectors u and v. We are just writing general this vector general. That this vector has entries v1 and v2, and the second one has entries v2, v1 and v2. The first has entries v1 and v2. So we need to prove that it satisfies this axiom. You can just prove from left hand and then check. You can show if the result in the left hand equal to the result in the right hand. So starting from the left hand, which is this one, and you have already supposed that this is u and this is v. You just substitute them here, u and v. And remember, we have said u had these entries and v had these entries. We have substituted them at the place of u, vector u and vector v. And summing up them, you get this one here. So, refer to the definition that if this vector is mapped from here in the next the result will be of x minus y at the first entry, the second entry will be x plus y, and the last entry will be twice the first entry. So here we are going to do the same. Here we are going to assume this as values for x, this is x, and take it minus y. That's why you're taking this one and this one. You're getting this one. And then we are summing up this and this one, and twice the first entries as elements v1 and v1. After multiplying the result here. So again, you can check for the right hand side. First substituting v here in the transformation, and then plus t, the transformation of v. We substitute the entries for u and entries for vector v. After substituting, we refer the definition we have given, which is this one of this transformation. Now, for this one, for only this one, it is this one and this one, the first entry, the second entry, we are summing them, and the third entry, we are taking just twice the first entry, as well as this one, which gives this one. And summing up this, you will see that this result is the same as the result we obtained from the left-hand side. And because all these are satisfied, then the first axiom is satisfied. Okay, the second axiom, we have just one vector, which is be an vector in R, which we have to have R specific, and C is a scalar or an real number. We need to prove this one. Also, we can start from the left hand side and then we go to the right hand side. Starting from the left hand side, we start T of C times U. C is a scalar. And multiplying this C with every entry of the vector U, we get this one, which is T of this vector after multiplying the scalar of the vector U. And then we refer the definition of our vector we have given, which is this one. So we take this one and this one, get the first entry and adding them, and then twice the first entry get this one. Now we can go to the right hand side to see if they are giving the same answer. So this is C outside, then the transformation of U itself. Refer the definition of this transformation. It's just the first entry is U1 minus U2, then the second entry is summing up, and the third entry is twice. Here we are supposed to have 2 here. Twice the first entry of this one. Of course, from there, if you remain with just on this one, we'll see here. If you multiply, we get the same answer here. So, and therefore, we have shown that this transformation is linear because it has satisfied the two axioms of linear transformation. Okay, we have a theorem here. This is a linear transformation mapping from Rn to Rm. If this is a linear transformation, then there exists a matrix such that find the linear transformation of any vector p in Rn is the same as taking that matrix of transformation, called the matrices of the linear transformation times the vector. All of them will give us the same answer. And this matrix is called the matrix of the linear transformation M, because the linear transformation. We don't have enough time, we could have to prove this one. I give you an exercise to go and to prove this one. And also it has been proved in the given notes in the Moodle platform. Okay, let's see the last part. The last part is about kernel and range of the linear transformation. Okay, by definition, what's a kernel? What's a kernel? Let you have a linear transformation T. That's mapping from Rn to Rm, the two vector spaces. Then the kernel for T, or the kernel of T, denoted by ker_T, is the set of elements in the first vector space Rn that map into zero vector in Rm. In general, on summary, the kernel of T is equal to the set of vectors which vector v which are in the first vector space Rn, such that if you find the linear transformation of every vector here, which are here, some of the vectors which are here will give you as Rn. As well as image or range of the transformation, the linear transformation, denoted by IMT. Im of T is the set of image points in Rn. That is the image of the linear transformation T equal to all the vectors in the second vector space Rm, such that there are existing vectors in the first the first vector spaces, for which if you find the linear transformation, sorry, it's supposed to be T, the linear transformation T of these vectors in Rn will give the vectors this U in Rm. Let's go to see an example. Okay, dear students, let's continue. Let's see this example. Let T, that's mapping from R3 space to R2 space, be a transformation defined by T of a vector which has entries x1, x2, and x3 will give us this vector. So let's say we have given this one. So A, we are asked to show that T is a linear transformation. B, we are asked to find the kernel of T. And lastly, C, we are asked to find the image of T. Okay, let's start with A. To show that T is a linear transformation, this mapping, we need to show if it satisfies the two axioms. The first axiom, we need to show that For all vector u in R3 space here, this property is satisfied. Okay, this property has two sides, left hand side and right hand side. So to show that this property is satisfied, we need to check both of the left and the right hand side if are equal. Start with the left hand side, which is t of u, vector u plus vector v. Here we get t of vector u, which are the entries, three entries. Three entries, u1, u2, and u3. Also plus vector v, which are three entries, u1, u2, u3. Okay. We sum these two vectors, we get vector u1, and I mean a vector is entry u1 plus v1, and u2 plus v2, u3 plus v3. From the definition of the given mapping from R3 to R2, here, what you are going to get here from the definition, referring the definition, we get that the definition tells us the first plus the second. So we are adding this and this one. u1 plus v1 plus v2 plus v3. And this one will be 2x1, what the first entry, negative 2 u1 plus v1 plus x2. x2, we are adding the second entry, which is u2 plus v2 plus, minus the third entry, here x3, which is u3 minus v3. So, in general, we are going to get u1 plus v1 plus u2 plus v. This is u2. This is u2. v2 plus negative 2 u1 minus 2 u1 plus u2 plus v2 minus u3 minus v3. This is t of vector u plus vector v. That's the left hand side. Let's check the right hand side. Okay, students, allow me to do this one so that our question may still be here. In the second axons, we need to show that we need to show that for all vectors u, let's call it as entries u1, u2, and u3. Okay, sorry. We haven't yet shown the left hand side. The right hand side. This was the left hand side. Okay, let's show the right hand side. The students, right hand side, which t, we need to show that t of u first plus t of v, vector v, will give us the same result. So, allow me to do this plus here. So here, referring from there, we have t of u1, u2, u3, plus t of v1, v2, and U3. Now, remember, we find the definition here. Here, we are getting U1 plus U2. And here is negative 2. U1 plus U2 minus U3. Plus, for this one, we get U1 plus U2, negative 2, U1 plus U2 minus U3. Okay, let's add these two vectors. Shall we get the same we obtained in the left hand side? Let us check. Okay, adding two vectors, we are getting U1 plus U2 plus U1 plus V2. Look, the first entry has become the same. And then taking this one with this one, we get negative 2 U1 plus 2 U1. Let us just finish it here. And this plus U2 plus U2. This one plus this one. And lastly, minus V3 plus V3. You can see this one lift the right hand side equal to the left hand side. And therefore the first axiom is satisfied. Let's see the second axiom to finally show that this is a linear transformation. The second axiom needs us to show that we need to show that for all vector u in R3 space, let's say u at entries u1, u2, and u3, and characteristic and for every scar as a real number, then T of U times C equals T of U itself. So let's start from the left hand side. From the left hand side, we take T of C of U. Now, this here, it's T of what's vector U? That's entries U1, U2, U3. It's T of C U1, C U2, C U3. And now, we find the definition of the linear transformation, the transformation we have given. So we can write this as C U1 plus C U2. And then the second entry is negative 2 C U1 plus C U2 minus C U3. This is for the left hand side. Let us check for the right hand side. For the right hand side, we need to check if also this one will give us the same as which are given by this one. So C T of vector U. Sorry. Here, C, the transformation of these which is U1, U2, U3. Now to C, by definition of this one, we get U1 plus U2, and then we find the definition of U2, U1 plus U2 plus U3. If you multiply C inside here, If you multiply C inside here, you get that this is it. It is C U1 plus C U2, and multiplying C down here, it is negative 2C U1 plus C U2 plus C U3, which is the same as this one. And therefore, since the two axioms are satisfied, now this is a linear combination. This is a linear transformation. Okay, that was just for part A. Let's see part 2, which is B, to find the kernel of the linear transformation T. Okay, we said from the definition, the kernel of T equal to all vectors U, vectors U, in R3 space, such that the transformation of U equal to a zero vector in R2. Okay, dear students, from there, T, the kernel of T, equal to, let U be a vector with entries U1, U2, and U3, which is R3 space, such that T of U1, U2, U3 gives us a zero vector, which is R2 space. Is R2 space. So it's just a vector this way. And now let's find this vector, this solution. Now U1, U2, U3, such that the definition of the linear transformation is, we are referring this one here, U1 plus U2, negative U1 plus U2 minus U3 is equal to a zero vector of two entries. Okay, let's make it take another marker pen. And now here, continuing with this one here, you get U1, U2, U3. Or we can just solve this one to find the condition. Let's just solve this one. That's here, U1 plus U2 equal to 0, and 2, U1 plus U2 minus U3 equal to 0. So, solving this simultaneous to find this condition here, I solved it here using, you can solve it by using any method. So, from my solution, I obtained that you can solve it by using any solution or any method. Okay, let me just write it generally. The kernel of T equal to U1, U2, U3 in R3 in R3, such that U1 plus U2 equal to 0 and negative 2, U1 plus U2 minus U3 equal to 0. This is the kernel 4, 14. Okay, my dear students, next we are going to find the image. We find the definition and do the same procedure we have done finding the kernel of the linear transformation. I give you this one as an exercise to do. Okay, my dear students, after looking the kernel and the image and the general idea of the linear transformation, this was the part for concluding our lecture. Thank you so much for your listening.